Hello everybody and welcome to Unit 4, Lesson 5. This is Ms. Meyer. Today we're going to go ahead and look at modeling with exponential and log equations. Your learning target is that you can use formulas to solve application problems involving radioactive decay and exponential growth. Let's go ahead and look at exponential growth first. The formula that we're going to use is n of t equals n sub o e to the rt. This should look similar to what you guys have seen in the past, which was a equals p e to the rt. Maybe you remember Pert. Okay. So what does p or n sub o mean? That's your starting amount. Okay. A lot of times when you've used this equation in the past, it's been dealing with money. So it was your principal or your starting amount. N sub o will be our initial population size. E is the letter E. Okay. R is the relative rate of growth. It's how the population or your money is growing. Okay. And since it's growth, it's going to be a positive R. And then T is the time. Then N sub T, or A, is the amount of money that you have left after T years, or N sub T is the population you have after T years. Okay, so that's our equation that we will be using. Exponential decay, very similar. The only thing different is we have M's, because it's typically talking about masses, and your R will be a negative. Okay, and this is when we talk about half-life. Okay, so L of n, so R is equal to the natural log of 2 over H. And H is your half-life. Okay, so it's however many years your half-life is. But the population is M sub O, so your initial starting amount of mass, E, and then it's a negative R, and this would be your R value. T is your time in years. Okay, so you plug that in and you get out your mass, how much mass is left. So example 1, we have the coyote population has a relative growth rate of 8% per year. It is estimated that the population in 2000 was 18,000 coyotes. Okay, it says estimate the coyote population for the year 2014. So the first thing is we are using our equation for growth, okay? And our growth equation was n of t equals n sub o e to the r t. Okay, so the way we're going to figure this out is n sub t equals, we start out with n sub o. What's our population we started with, or how many coyotes did we start with? 18,000. E to the r. R is our growth rate. Now you have to remember, you always put this as a decimal. It's currently a percent, so I have 8%, and in order to make it into a decimal, I take and I move my decimal to the left 2 units, or two times. So this is 0.08. Okay, so my R is 0.08, so it's 0.08. And now you just have to be careful. Our time, if we started out in 2000, to go from 2000 to 2014, that's 14 years, so our T is 14. And then from here, we just need to go ahead and type this in to get our coyote population. So we have 18,000. Then E is either above your division sign or above your ln. If you do the one above the ln, it naturally provides you with an exponent. Okay, so it's E to the 0.08 times 14. All right, so here is the answer we have. We have 55,167.37566. So we have to think about our answer. Our answer is the population of coyotes. Can you have 0.37566 coyotes? No, you cannot. So we follow rules of rounding. Okay, we round to the whole number. So I would look, if I want to round to this decimal place, my ones place, I would look here. The 0.3 tells me to stay the same. So I would have 5,167 coyotes. So my N of 14 after 14 years is equal to 55,167 coyotes. Okay, so there's A. B, how many years will it take for the coyote population to be 100,000? So now I'm trying to find years. I'm trying to find T, so I don't know what T is here, but I do know how many coyotes I have. I have 100,000. So I would have 100,000 equals 18,000. E, my rate that they're growing is still 0.08 T. Okay, so now I need to solve this. In order to solve, I always need to get E by itself. So I would first divide by 18,000 on both sides. So this cancels. Okay, I'm just going to reduce this. I have 3 zeros. Those would all cancel. So I have 100 over 18. I'm just going to leave it like that for now. 100 over 18 equals e to the 0.08 t. Now that I have e by itself, I want to get rid of it so I can solve for t. The way we get rid of e is to natural log, because they are inverses and they cancel each other out. So I have ln of, it's all of 100 divided by 18 equals 0.08 t. Now my last step to get t by itself would be to divide by 0.08. So this all cancels. So t equals ln of 100 over 18 all divided by 0.08. I highly, highly encourage you all to type this in. That is the hardest part sometimes, is just typing it in. Okay, so we have ln and then 100 divided by 18, and now that's all inside the ln, so I'm going to end that parenthesis. Then I'm going to go ahead and divide that by 0.08. Okay, so we are solving for t this time, which is years. So we're going to round to 3 decimals when it's years. Okay, so I have 21.434. Now if I'm rounding to my third decimal, I look to the fourth one. This 9 tells me to round up. Remember, if this is a 5 or higher, we round up. So it'd be 21.435. 21.435, and then what is our time labeled in? Years. So it's going to take 21.435 years for our coyote population to get to 100,000. Okay, so here's example 1. Example 2. We have a culture of bacteria and it doubles its size every 3 hours. If the culture is started with 1,000 bacteria, find the function that models the number of bacteria after t hours. Okay, so what we have here is we have growth, and so our growth was n of t equals n sub o e to the r t. Okay, and I'm just going to fill in what I know. We know that we started with 1,000 bacteria, so that's my n sub o. Do I know my rate? I do not. No, it doubles, but I don't know my specific rate that it's growing at. But I do know it doubles. So if I started with 1,000 bacteria, I would double it. So then I know I end with 2,000. Okay. I don't know R, but I do know T. T is 3. Okay, so I'm going to plug in all this information. So I have 2,000 equals 1,000 e to the R times 3. And in order to find the function, I would need to know my rate. So I'm going to solve this for my rate. Same steps as before. In our last problem, we would divide both sides by 1,000. My zeros cancel. I have 2 divided by 1, so I have 2 equals E. I'm going to write 3R. Then we go ahead and take the natural log on both sides. So I got ln of 2 equals, ln and E cancel. So I have 3R. And then to solve for R, I would divide both sides by 3. So I have ln of 2 divided by 3 equals R. Okay, so there is my rate. That's awesome. Now all I have to do in order to write my equation is plug in my rate. So I would have n of t is equal to 1,000. So many we're starting with e to our rate, ln of 2 over 3 t, because it says after t hours. So that would be my equation for example 2. Okay. One thing that you guys could take note of is if it is doubling, okay, your rate will be ln of 2 over d, and d would be how long it takes to double. Okay, so in this case it takes 3 hours, so your rate would be, the d would be 3. If it said I doubled every 12 hours, it'd be ln of 2 over 12. Okay, very similar to your decay function. It's ln of 2 over h, your half-life. Okay, except for it's ln of 2 over d, your doubling time. So that's the shortcut. You can always do it this way, but just as a heads up. All right, example 3. The half-life of selenium-83 is 25 minutes. If there is 10 gram sample, what amount will there be after 80 minutes? Okay, so in this case, we're doing half-life. So we got m of t is equal to m sub o of e to the negative rt. And r is equal to ln of 2 over h. Okay, so that is just taking it from our previous slide. So let's start setting this one up. We got m of t equals m sub o. That is how much we started with. We started with 10 grams. E to the, now it's decay, so it's negative, ln of 2 over my half-life. And in this case, my half-life is 25. And then we'll have t. Okay, so this would be my equation for any time. Now we're going to do it for 80 minutes. Okay, just be careful, you guys, with labels. Make sure they're always the same. So these are both minutes, so that's great. So now I'm going to find m of 80. That's going to be 10e to the negative ln of 2 divided by 25 times 80. And once again, hardest part, you guys, is typing it in. So let's go ahead and do that. So we have 10. Then I have e to the, was it negative? Well, was it negative? Ln of 2. And then our half-life, I didn't get in the exponent. Clear that out. 10 e to the, there we go, negative ln of 2 divided by 25. So it's all in my exponent, and then I need to multiply that by 80. All right, and I would get 1.088, and this one would tell me to stay the same. So 1.088, okay? So 3 decimals is good unless the directions say otherwise, you guys. If the directions don't say, feel free to do 3 decimals, okay? So we would have, when I typed it in, it was 1.0, yes, 88. And then we can have that much in grams. It doesn't have to be a whole number. Okay, so that is the first one. Okay. Now this one says, how long will it be when there's 1.25 grams left? So in order to solve that one, I am getting out to the end amount, so I'm going to plug it into here. So I'd have 1.25 equals 10 e to the negative ln of 2 over 25t. Same steps as before, divide both sides by 10. Okay, if I take 1.25 divided by 10, I get 0.125 equals e to the negative ln of 2 over 25t. Now in order to get e by itself, I would ln on both sides. So I have ln of 0.125 equals negative ln of 2 over 25t. Now to get t by itself, what I would do is multiply by the reciprocal of this. That's the quicker way, but maybe we'll just take a few steps to see it out. We would multiply first by 25. But if you wanted to speed it up, you could. So I have 25 ln of 0.125 equals negative ln of 2t. So to get t by itself, divide by negative ln of 2. Okay, so t is equal to, got to type all of that into our calculator. 25 ln of 0.125. Make sure you end the parenthesis and then divide by negative ln of 2 in that parenthesis. And you should get 75. Okay. So t is equal to 75, and then I should find my label for t. T is being labeled in time minutes, 75 minutes. Okay, so that is example 3. All right, your turn. I would recommend pausing and doing this problem on your own, and then come back and I'll work through the solution. Okay. So your turn. In 2000, the population of the world was 6.1 billion, and the relative growth rate was 1.4% per year. What is the estimated population of the world in the year 2050? How many years will it take for the population to hit 15 billion? All right, so we have 2 different questions going on here, so let's just start with the first one. What is the estimated population of the world in the year 2050? Okay, so we are growing, so then that is our n of t equals n sub o e to the rt. Okay, so I'm just going to write our general equation. N sub t equals, we are starting with 6.1 billion, so we can write 6.1 e to the relative growth rate. Just got to put it as a decimal. So move it over 2, so it'd be 0.014, so 0.014 t. Okay, so there's my general equation for any time. We want to know specifically the year 2050. So now be careful. We started with in 2000, so how many years is it from 2000 to 2050? It's 50 years, so we plug in 50. So it's 6.1 e to the 0.014 times 50. And I would go ahead and type that into my calculator. 6.1 times e to the, I'm blanking, what do we have there? 0.014 times 50. All right, and I would get, I'm going to round to 3 decimal places, 12.2838. So this 8 would tell me to move up to 4. So 12.284. So n of 50 equals 12.284. And then I'd be careful. I can have decimals because this is billion. 12.284. Okay. So there it is. Just make sure you put that label of billion. That's how many people there would be in the year 2050. All right, now how many years will it take for the population to reach 15 billion? So now I'm going to take my original problem, okay, equation right here, and I'm going to say, well, when does it equal 15? So I have 15 equals 6.1 e to the 0.014 t. So same thing, in order to get rid of, to be able to get rid of e, I first have to get it by itself, so divide both sides by 6.1. I'm going to leave it as 15 over 6.1 equals e to the 0.014 t. Now in order to get rid of e, or to get my t out of that exponent, I ln on both sides. So I have ln of 15 over 6.1 equals 0.014 t. And then to get t by itself, I would divide by 0.014. All right, so t is equal to, now let's type it in, ln of 15 divided by 6.1. ln of 15 divided by 6.1. Then it's important, you guys, that's all inside the ln. You got to end that parenthesis. Then you're going to divide again by 0.014. And we're getting out time, so we're going to round to 3 decimal places. This 6 would tell me to go up to 9. So 64.269. 64.269. And then my label for my time would be years. So we're going from 2000 to 2050. So that's how many years it would take to get to 15 billion. Which makes sense, right? Because in my first problem, I plugged in 50 years later. It was 12.28. So it should take more than 50 years. It's taking 64 years. Okay. Another your turn problem. I would highly encourage you once again to pause the video and go ahead and try this one, then come back. Okay. So we have polonium-210, and it has a half-life of 140 days. Suppose the sample has a mass of 300 milligrams. Okay. Find the function of the amount remaining after time t. So we are doing exponential decay. So m of t is equal to m sub o e to the negative rt. And remember, r is equal to ln of 2 divided by our half-life. Okay. So m of t equals m sub o. How much did we start with? 300 milligrams. Then it's e to the negative, it's ln of 2 divided by our half-life. The half-life is 140 days t. Okay, so there is our equation for at time t, anytime. Okay. B says find the mass after 1 year. Now here is where we need to be careful. This is days, this is a year. So we need to make this be in days. Okay, so how many days are in a year? Let's go with it's not a leap year, 365 days. So in order to figure this one out, we just have to go m of 365, and I'll plug it in. So I have 300 e to the negative ln of 2 over 140 times 365. So let's type that in. So we have 300 e to the negative ln of 2 and the ln of 2 divided by 140, and then you take that times our number of days, 365. Okay, we're talking about a milligram, or we're talking about a substance, which is milligrams, so you can have a decimal. Okay, so we're going to go 3 decimals out. So if I look to my third decimal, I check out the 1, it's the next one, it's a 1, so it says to stay the same. So it's 49.237 milligrams. So m of 365 equals 49.237 milligrams. Okay, so there it is. And then it says, how long will it take for our sample to decay to 200 milligrams? Okay. One thing I would take a note of, you guys, is it takes 365 days and we are only 49.231. So my answer should be less than 365 days. So something to kind of keep up, you can use your answers to help you out. So we want to know when it's 200. So I'm plugging that in here because that's my final amount. So I have 200 equals 300 e to the negative ln of 2 over 140 t. So we got to do is divide both sides by 300. The zeros cancel, so I'm left with 2/3 equals e to the negative ln 2 over 140 t. So you guys, this is all up in the exponent. It's kind of hard for me to write, sorry. Up in the exponent. So the way we get rid of the way we get rid of e is ln. So I have ln of 2 over 3. That cancels. Now it's out of the exponent. So I have negative ln of 2 over 140 t. Times both sides by 140. So now what do I have? I have 140 ln of 2 over 3, all in parentheses, equals negative ln of 2t. So then to get t by itself, I divide by ln of 2. Negative ln of 2, I should say. So let's cancel. So I need to type this into my calculator to get t. So t is equal to 140 ln of 2/3. 140 ln of 2 divided by 3. And the parenthesis divided by negative ln of 2. We get, rounding to 3 decimal places, this is a 4. Sorry, we're looking to the third one, which is 4. This is a 7, so it's bigger than 5, so it tells us to go up. So it's 81.895. 81.895. And then our time would be in days. So is that less than 365 days? Yes, it is. Okay. So there is our second your turn problem. And that will go ahead and do it for our lesson 4.5.